Sara Maloni. And actually, I'd like to use this opportunity to talk a bit more broadly, not only about what we did with Jeff and Sara, but about other results and other questions open in this area, because it's a, I'll try to show you that this is an old area. They are old questions, but we don't have all the answers yet. So that's funny. So the story starts with this man called Jakob Steiner, who was a very important mathematician in the beginning of the 19th century. And Steiner worked on what could be considered the modern theory of polyhedra. People have been studying polyhedra since, at least since Euclid, probably much earlier. And, Euclid did this wonderful work on the classification of regular polyhedra, but he looked at those polyhedra in a very specific way, mostly as regular objects. And Steiner discovered that you could look at them in a much different way. And there were lots of questions that the Greek mathematicians had never thought about that Steiner thought about. And Steiner wrote this book on polyhedra. This is the book. It looks pretty old. It is pretty old. And he asked a number of questions. And most of the questions were, by today's standards, quite easy and have been answered very long time ago. But a few of the questions were actually not so easy. So, for instance, one question that Steiner asked is, what are the possible combinatorial types of polyhedra in Euclidean space? Yeah, and that looks easy, but it wasn't easy. I'm going to show you the answer, but it took almost a century to answer it. And then another question that he asked is this question 77, which I wrote here for those who understand Old German, sorry. And I actually tried to translate it too, just in case. So the question is, what are the possible combinatorics of polyhedra which are inscribed in a quadric? And so what is a quadric here? This is all in R3, and a quadric is a surface of degree 2, right? So I'm going to show you exactly what we mean by this. And what Steiner actually meant by inscribed in a quadric is really he wanted the vertices to be on the quadric. That's all the things he wanted. And there is a very beautiful aspect to this question, which I think was implicitly known to Steiner already. And the reason this question is nice and simple in a way is that it is projectively invariant. So what do I mean by this? If you have a polyhedron, you apply a projective transformation of Euclidean space, you find another polyhedron. And if you have a quadric, you apply a projective transformation to this of Euclidean space, you also find another quadric. So actually, this is not a question about Euclidean geometry. It is a question of projective geometry. And the point is that in spite of recent progress, the question remains more or less, partially open. There are parts of the question which are still open. So let me first remind you of very simple things. So in fact, there are only 3 quadrics in R3 up to projective transformation. So what I really mean by this is that there are 3 quadrics in projective space after projective transformation. So one of them is the sphere, or in fact, any ellipsoid is projectively equivalent to a quadric. If you have any ellipsoid in R3, you can apply some projective transformation, you find a sphere. You have this 2-sheeted hyperboloid, and in fact, it is also projectively equivalent to the sphere. That is not completely obvious, but if you have a sphere in Euclidean space, maybe I can make a drawing. There is a projective transformation that sends, so this is the sphere. I'm going to choose this plane that cuts the sphere in 2 and apply a projective transformation sending this plane to the plane at infinity. And therefore, if you do this, you find exactly this 2-sheeted hyperboloid. So it is projectively equivalent to a sphere. Then you can also consider the 2-sheeted hyperboloid. And this one, there is no way to make it different from itself by a projective transformation. You can apply any projective transformation. It will always look like a 1-sheeted hyperboloid. And then there is one degenerate case, which is this cone. And the cone, again, you can send this point at infinity by applying a projective transformation, and you'll find a cylinder. So in fact, there are 3 possible cases: the sphere, or the 2-sheeted hyperboloid, the 1-sheeted hyperboloid, or the cone, which is also the cylinder. So there's basically, we're going in this talk mostly to set aside this conic and not think about it too much. I'm going to say a few words about it because it's actually very interesting. So we have two cases to consider. And in fact, there are two different questions we can read in the Steiner question. The first one is if we only consider polyhedra which are inscribed in the modern sense in the quadric, which means that the vertices are on the quadric, but the polyhedra do not intersect it outside the vertices, so they're contained in one side of the quadric. And the other situation is what we call polyhedra weakly inscribed in the quadric, which means they have their vertices on the quadric, but they also cross it. So when we say they are weakly inscribed, we mean they are not strongly inscribed, so they have to have some intersection outside the vertices. So if we forget about the degenerate case, we have four problems here. And what I'd like to say is that we have a pretty good answers to Steiner's question in 3 of the 4 cases, and some questions are still open. Is this clear? Yeah? Okay, so the first thing I'd like to say is that, as I mentioned, Steiner asked what are the possible combinatorics of polyhedra in a Euclidean free space. And the answer was given by Steinitz almost 1 century later. It's a very classical theorem of combinatorial geometry. So if I give you a graph and I ask you whether there is a polyhedron with this graph as a one skeleton, so the graph realized by the edges and vertices, and this is possible if and only if this graph is planar and free connected. So free connected means you cannot cut it in two pieces by removing free vertices. Yeah. So that's the first. Oh, planar means you can draw it in a plane without self-intersection. That's, if you are in this situation, you have any polyhedron, you can take a vertex in the center and project radially to a fixed plane, and you will find a graph in the plane. So yeah, the polyhedron, combinatorics, I mean the one skeleton of the polyhedron. So no, you don't want to do that. You want to have situations where you allow for graphs which are more complicated, which have more than the bigger degree at some vertices, and you also want to allow faces that have more than 3 edges. Otherwise, it's a very specific case. Yeah. 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 I've always been convex, absolutely. You're right. I very often consider non-convex polyhedra, but that's not so common. In this setting, they're all convex. Yes, absolutely. Yeah. In this setting, that is a necessary condition. Yes. Okay. Yeah. So now the Steinitz also gave the first example of a polyhedron of a combinatorics, a graph that cannot be realized as the one skeleton of a polyhedron inscribed in a sphere. So he gave the first, if we go back to this question of Steiner, he gave the first example where you had a combinatorics that could be realized for some polyhedron, but not inscribed in a sphere. So it meant that this question was actually not empty. And in fact, now we know a much simpler example, and this is even a more general example. It is this polyhedron, which is a cube with one vertex truncated. So you take a usual cube and you cut off one vertex. So this is what we call the truncated cube, or one vertex truncated cube. And the remark, which is basically, it follows from a result of Bobanco and Souris, or a remark of Bobanco and Souris, this cannot be realized with its vertices on any quadric. So the reason of this is very beautiful. I'd like to give one proof in this talk. So it's very simple. So it relies on this result of Bobanco and Souris, that if you have a cube with 7 of its 8 vertices on a quadric, then the last vertex must be on the quadric also. That's a very simple elementary theorem. And if the quadric is a sphere, it's a very old theorem, or it's equivalent to a very old theorem, which is called the Michael 6 circle theorem. I can draw this for you if you want, but it's very classical geometry. And Bobanco and Souris remarked that this can be extended to any quadric. And you can prove it by, very simple algebraic transformations. So now the point is, if you take this truncated cube, assume that 7 of the 8 vertices, the non-truncated vertices, are all on a certain quadric cube. Well, this means because of their theorem that the 8th vertex must be on the quadric too. But then this means that those edges, they cannot intersect the quadric in a third point because the line intersects the quadric in only 2 points at most. So therefore, there is no way you can realize this truncated cube with its vertices on any quadric. Yeah. So that's a starting point, and I'll show you that in one case, that's the only thing we know. There is one example that cannot be realized with its vertices on the quadric, and that's that cube. Okay. So now I'm going to try to give you results. So the first one is about polyhedra inscribed in a sphere. So what I mean here again is I take a sphere and I want to understand the possible combinatorics of polyhedra with vertices in a sphere and which are sitting in the sphere. And there is a pretty good answer that was given by Hodgson, Rivin, and Smith in the early 1990s, 93, I think. It's a very beautiful theorem, but it's not completely satisfactory for a reason that I'm going to tell you. So the statement is the following. So you take a graph gamma, you assume it's a free connected planar graph, of course, otherwise you cannot hope anything. And then you're going to call gamma star its dual graph. So what do I mean by the dual graph? So here gamma is the blue graph, and the dual graph has one vertex for every face of gamma, and it has one edge for every edge of gamma, and the edge connect the vertices of the dual graph, which are dual to the faces on each side of the edge. Yeah. So it's a very simple and natural definition. So you have this blue graph gamma, and the dual graph is this gray graph gamma star with the green vertices. So now they look at, Hodgson, Rivin, and Smith, they look at this graph and they say, I'm going to define a sequence, a set of equalities and inequalities associated to this graph. So for every face of gamma star, which means any vertex of gamma, they sum, so they associate, variables to every edge, and they sum the edges which are on the boundary of this face of the dual graph. Or in other terms, they sum the variables corresponding to the edges adjacent to the vertex of the primary graph, of the primal graph. And this sum, they want this to be 2 pi. So that's the first set of equalities. And then they have another set of inequalities, and now they take a path in the dual graph. And this path is anything that is not the boundary of a face. It's more complex than the boundary of a face. And now here they want the weights to sum up to something bigger than 2 pi, strictly bigger than 2 pi. And the theorem that they proved is that if you have a free connected planar graph, then it is the one skeleton of a polyhedron inscribed in a sphere if and only if there is a solution to this problem, right? There is a function from the set of edges to 0 pi satisfying this set of equalities and this set of inequalities. Yeah. So if you think of it, it's a very nice result from one point of view, and it's also not completely satisfactory from another point of view. So what is really nice, what is not nice maybe first, is that it's not explicit. So it's not a combinatorial description. You'd like to have a combinatorial description, and this is not a combinatorial description. You have to solve a bunch of equations. What is really nice, on the other hand, is that it's a good set of equations that can be solved in polynomial time. So computationally, it's quite good. But still, I think there is a question that remains here, which is there a combinatorial characterization of graphs that can be realized? That's not clear from their statement. And then I'm going to tell you, of course, where this comes from, because this comes from a place where there is beautiful geometry. This comes from hyperbolic geometry and the geometry of ideal polyhedra in hyperbolic space. Okay? Any questions? No? Okay, so now I'm going to switch to the next statement, which is a result that I'm supposed to explain here, which is a paper we wrote with those young people. Now they're not as young, but they used to be young like this when we worked on this. Sara, Maloni, and Danciger. And this is about polyhedra inscribed in a one-sheeted hyperboloid. So, and again, there is we have a result and we have also a question. So the statement is the following. So again, I take gamma, a free connected planar graph, and I claim it's the one skeleton of a polyhedron inscribed in a one-sheeted hyperboloid, if and only if, first, well, there are two conditions. The first condition is that it satisfies exactly the same conditions as the one in the result by Hodgson, Rivin and Smith. So those are the existence of a solution to those set of equalities and inequalities. And then there is a second condition, is that it has to admit a Hamiltonian cycle. So the good point is that it looks like it's a slight precision compared to the spherical case. What is very annoying for me is that we have no reason to understand why the same condition comes up in the two cases. Why it is exactly the same condition one that comes here. We can prove it. I mean, it's a consequence of the proof of what of some characterization, but we have no explanation of it beyond the proof. So that's a bit annoying. So yeah, where is the Hamiltonian cycle? So I can tell you this is going to be easier, but basically I'm going to explain this a bit better later. But the idea is that you look at this polyhedron, and there is a notion of line here that doesn't intersect the quadric. So if I anticipate a bit, those are actually light lines in the anti-de Sitter space. And those lines, they always intersect the polyhedron twice. So there is a bunch of faces that are oriented to the future and a bunch of faces that are oriented to the past. And this Hamiltonian cycle, it is exactly the curve that separates the faces oriented to the future from the faces oriented to the past. Yeah, I wanted to say this later, but that's good. Okay, and another remark is that this looks, as good as the spherical case, but it's not as good at all, because in the spherical case, you could check those conditions in polynomial time. But now it's not the case at all, because checking that a graph has a Hamiltonian cycle is NP complete. So it's much more complicated to check this condition than to check the spherical condition. So things look alike, but they also look different in a way. Yeah?
This implies that being inscribable
Hyperboloid. Yeah, exactly. Yes, absolutely. No, that's the point. And also, yeah. Okay, if you know a bunch of things, you can understand it. Yes, you can, because the point is that if you have realization, you can get a realization that is very flat, and this realization, which is very flat, can be then deformed to realization in a sphere. That's yeah. Okay, and one thing I'd like to say is that the exact same result applies also to the cone. But the geometry that is behind it is quite different and quite interesting. So I'm going to say a word about this later. Now, I'd like to state another result, and then state a question. So now, what about polyhedra which are weakly inscribed in a two-sheeted hyperboloid? So again, what I mean by this is, I'm still looking at a sphere projectively, but now in Euclidean space, my sphere looks like this. It looks like a two-sheeted hyperboloid. And you can have polyhedra which are inscribed in this in the sense that the vertices are on this object, but they are weakly inscribed in the sense that they actually don't sit on one side. So this is actually quite possible. And you can also ask, following Steiner, what are the possible combinatorics of those objects? And this is a question we answer with Hao Chen, who is here. The answer is quite different. In fact, it is quite similar at some level, but in fact, what is nice is that in this case, we have a completely explicit combinatorial description. And the statement is that, again, you have a free connected planar graph, and it is the one skeleton of a polyhedron, weakly inscribed into a sphere. So in other terms, inscribed in this two-sheeted hyperboloid, if and only if there is a very combinatorial description which is satisfied. So first, you can cover every vertex by two disjoint cycles. So that's exactly what is in condition C1. And then the other condition is that there is a cycle, which is visiting all the edges and doing something relatively simple. So let's, this is a special case where you have only one vertex in one side, and otherwise it must be doing this. It must be doing going from one cycle to the other one, back, and then cycle, back, cycle, and so on. So that's a very, what am I saying? Yes. Yeah. So that's a very combinatorial distribution, and you can check it, again, quite explicitly. Yeah. And then the last case is polyhedra which are weakly inscribed in a one-sheeted hyperboloid. So again, the picture is that you have this possible description for a one-sheeted hyperboloid. You might have polyhedra that have the vertices on the hyperboloid, but they don't sit on one side. So it's going to be something like this. I'm sorry, my drawings are extremely bad, and I really have trouble doing better than that. But that's also a possibility. And that's completely open, because basically the only thing we know is that there is one example that cannot be realized in this way, and that's the truncated cube that I showed at the beginning. Otherwise, I don't know anything about this. I don't know any other example, and I don't know any characterization. I know some, necessary conditions, but I don't know if they are empty or not, except for the truncated cube. Okay? So now I should tell you a bit about what the proofs rely on. And the proof relies on the study of what we call ideal polyhedra in geometric spaces. So what does this mean? Well, we really want to interpret those inscribed polyhedra as polyhedra which are contained in a certain geometric space. And the fact that the vertices are on the quadric means that they are at infinity, and what we call ideal vertices. So we are going to deal with ideal polyhedra in different spaces. And the main results will follow from the description of the possible dihedral angles of those polyhedra. And what we're going to look at differs in the different cases. So if we look at polyhedra inscribed in a sphere, this relies on the dihedral angles of the hyperbolic space H3. And then the result follows basically from results of Andreev in the 1970s and Rivin in the 1990s on the possible dihedral angles of ideal polyhedra in hyperbolic space. Now, if you look at a one-sheeted hyperboloid, we're going to be in what is called the anti-de space. If we look at polyhedra in a cone, we look at a more exotic space, which is called half-pi space, HP3. And if we look at polyhedra which are weakly inscribed in a two-sheeted hyperboloid, and that's the case that is there, it's really polyhedra in what is a natural extension of hyperbolic space by the de Sitter space. I'm going to show this in the next slide. I think basically it's very geometric in a way and relatively simple. So in each case, again, those ideal polyhedra will have their vertices at infinity. Yeah. Yeah.
It's an if and only if statement. Is one direction easy? Which direction is hard, or are both directions hard?
Okay, so if you know the geometry, I think it's not that hard to prove that the conditions are necessary. Yeah. Although I don't say it's easy, right? It takes some work, but it can be done. I think what is more difficult is to prove that they are sufficient. And there you have, I'm going to tell a few words maybe about the proof, but there's some technology involved.
Yeah. Then it's enough to produce some and you can produce these ideal. So that's not the way.
No, I think it's much more difficult to produce the non-ideal ones than the ideal ones. The ideal ones are much simpler to understand because, at least, especially in the hyperbolic case, things are much simpler in a way. I can try to tell you more about this later. Yeah. Okay, so what are those spaces? So hyperbolic space, that's the the space that has been known for the longest time. You can see this as a sort of sphere in the Minkowski space. So Minkowski space is the space of special relativity. So this is R4 with a scalar product of signature 3, 1. So basically, I didn't write the definition. So I have to define this R31. So R31 is R4 with the scalar product, which is the following. I thought I had given it here. So XX is minus dx0 squared plus dx1 squared plus dx2 squared plus dx3 squared. So if you have done a little bit of physics, you know that this is where special relativity plays a role. And now in this space, you can take the space of vectors with a square norm equal to -1, and the first coordinate, so here I call it t, positive, and this is going to be a one-sheeted hyperboloid, a connected component of the one-sheeted hyperboloid here. But this is a three-dimensional space. Now, we have other spaces that are almost as nice, and one is called the de Sitter space, and this is a space that is also defined as a subspace, as a subvariety in Minkowski space of dimension 4. But now you want to take the scalar product to be equal to 1. Yeah? And it's a complete space, geodesically complete space, but of curvature 1, but now it's a Lorentzian space. It's not Riemannian, it's Lorentzian. And it was discovered in the 1920s, as far as I know, by Willem de Sitter, originally as a model for cosmology. And what is really important for us is that it is dual to H3, and it's strongly connected to H3, and it also can be seen as a natural extension of H3. And I'm going to tell you a bit about this slightly later. And then we have the anti-de Sitter space. And the anti-de Sitter space, there is a typo here. It's the space of points in now R22. So R22 is the same space, but you put a minus in this position. So now you have two positive and two negative directions. You take the space of vectors with scalar product equal to equal to -1. And now you get another space which is Lorentzian, but of constant curvature -1. It was also discovered, I think, as a model for cosmology. And then we have this last space, which is used in the case of the cone, and that's called the half-price space. And it was discovered much more recently, as far as I know, although there are probably ways to see this earlier. And I think it also appears in the physics community in a way. But the way I heard about it is from the thesis of Jeff Danciger in 2013. And it's also, in a way, it's a space of constant curvature, but it's a degenerate space with signature 2, 0. So it's a 3D space, but at every point, the metric has signature 2, 0. So there is one degenerate direction, and it's a positive definite in the other directions. And this is useful for this story. Yeah? Okay, so now the point that is important for us is we have projective models of all those spaces. So those polyhedra inscribed in the quadrics, they can be interpreted as ideal polyhedra using a projective model. So what do I mean by this? I'm going to make a picture here of what we mean by the projective model for hyperbolic space. So we have this hyperbolic space in the Minkowski 4 space. So we have this negative direction, those positive directions. And we can take the plane tangent to the hyperbolic plane at the origin. And then we can project the hyperbolic space to this plane radially. Every point is sent to the intersection of the line going through 0 with this plane. Yeah. So this is a map that is sending the hyperbolic space to the ball of radius 1 in this horizontal plane. And it has this beautiful property that you can prove quite easily by a nice geometric argument, that geodesics in hyperbolic space are sent to line segments. To line segments. So every geodesic here is going to be sent to a line segment in this ball. So that's called the Klein model. It was discovered by Felix Klein in the 19th century, maybe early 20th century. And of course, now if you have any polyhedron inscribed in the sphere, you can interpret it as an ideal polyhedron in hyperbolic space using this Klein model. And this is really what we do. Now, another thing is that, of course, there is also a projective model of the de Sitter space. So why is this true? Well, what we can do, we can look at this de Sitter space as a quadric in the same Minkowski space, And now we can also do the same sort of construction, but for points in the de Sitter space, and specifically not in the whole de Sitter space, but only in the part above the horizontal plane through 0. So any point which is above 0 will have a line going through it that intersects this plane in exactly one point. And in this case, we have a beautiful projective model that extends the one of hyperbolic free space. So we'll have hyperbolic free space here and the de Sitter space outside. Yeah. And now I'm not going to draw this, but we have the same possibility for the anti-de Sitter space. And then we have a projective model which is in a one-shaded hyperboloid. And for the half-pi space, there is a projective model also in a cylinder or in a cone, depending on how you want to look at it. So there are different ways to look at those projective models, but they really play a big role in what we do. So using them, those ideal polyhedra, those polyhedra inscribed in a sphere or hyperboloid, they become ideal polyhedra in a corresponding space. Okay? So now, if I want to understand the statement of Rivin, Hodgson, and Smith on polyhedra inscribed in a sphere, I just have to know this theorem of Andreev and Rivin, which is that if I have an ideal polyhedron, an ideal hyperbolic polyhedron with one skeleton gamma, then the dihedral angles, and specifically I mean the exterior dihedral angles, that mean if they are 0, if the edges are flat. So they satisfy two conditions. So one is that for every vertex, the sum of the angles of the edges arriving at the vertex are 2 pi. And then another condition is that for every path in the dual graph, not bounding a face, so not corresponding to a vertex, an ideal vertex, the sum must be strictly bigger than 2 pi. And also, if you have any angle function satisfying those two conditions, it is realized on a unique ideal polyhedron. Yeah. So I'm not going to tell you exactly how to prove this, but one thing I'd like to say is that the way this was proved by Rivin is by using remarkable convexity properties of the volume of ideal polyhedra, and specifically of ideal simplices. So you have this property that an ideal simplex is determined by two angles, and the volume of the ideal simplex is a concave function, strictly concave function of those two angles. And this can be used in a very beautiful way, invented by Rivin and Carson and maybe other people, to prove the rigidity of polyhedra with respect to the angles and to prove this theorem. Yeah. Okay, so now let's go to ADS. And again, for ADS polyhedra, we have a very similar statement. So we take an ideal ADS polyhedron with one skeleton gamma. Then gamma admits a Hamiltonian cycle, small gamma. And the exterior dihedral angles satisfy a certain condition. So first, if you define those angles properly, they will be positive outside of gamma, and they will be negative on gamma. So that's maybe a question of how you define the angles, but I think that's really the natural way to do this. So again, this Hamiltonian cycle will correspond to places where the two adjacent faces are folded like this, while elsewhere they will be unfolded like this, more or less. And if they're folded like this, then the angle becomes negative. Then the second condition is that for every vertex, the sum is again equal to 0. And then there is a third condition, which is that for all paths in the dual graph, not bounding a face, and intersecting, oh, my notations are terrible. This should be gamma prime. Intersecting this Hamiltonian cycle twice, the sum of the angles must be strictly positive. So moreover, if you have any angle function satisfying those conditions, then it is obtained on a unique ideal ADS polyhedron. Yeah. So it's a bit like the previous statement of Andreev and Rivin, but the only difference is this Hamiltonian cycle. Yeah. So this statement extends exactly as it is to half-pipe geometry. So in half-pipe, you have a notion of angle, you have a notion of, so everything can be done in the same way in half-pipe. That's exactly the point, yes. Yeah. Yeah. No, 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 it's completely different. So that's the point, you know, basically there is a big difference between that in the hyperbolic setting, you have this convexity of volume, which is a, you know, big thing. And when we started this project, we wanted to use the same ideas, but they don't work at all because ideal simplices in ADS do not have this property. It's really not true at all. It's a complete difference between the two theories. And in that case, you know, hyperbolic geometry is simpler. In many cases, ADS is simpler, but in that case, hyperbolic geometry is simpler. So we have to use a completely different argument. And I'm going to try to say a few words about this. The first point is that we need to use the notion of duality, which I'm not going to describe so much. But I'd like to say that whenever we have a polyhedron in this, you know, quadric, for instance, we have a dual polyhedron, which lives maybe outside the quadric, basically which have faces which are tangent to the quadric at the ideal vertex of the first polyhedron. And this is also a convex polyhedron, but now instead of understanding the dihedron angles, we have to understand the edge lengths of the dual polyhedron, which are equal to the dihedron angles of the primal polyhedron. So this is what we need to understand now through this notion of duality. And then we basically use something quite completely magical, which was invented by Russian mathematician called Pogoryalov in the 70s. And there is a way to transform a rigidity problem from hyperbolic space or any constant curvature space, in fact, to a Euclidean space. And through this Pogoryalov map, we can reduce the rigidity of those polyhedra in ADS, hyperbolic, or whatever, to a problem of rigidity of convex polyhedra in Euclidean space, which is something that has been known for a very long time through, I mean, it was already proved by Cauchy, more or less, in the early 19th century. And then the whole argument that we use is what is called a deformation argument. So we consider the map sending a polyhedron to its dihedral angles. And we prove that this map is a local homomorphism, thanks to the rigidity result obtained by the Pogoryalov maps. And it is proper, therefore it's a covering map, and then we conclude that it's actually a homeomorphism. So it's a very indirect proof. There is no direct way that I know to actually find those realizations, but we know there is one, and it's unique for every given set of angles. And then we have a similar result applying to the dihedral angles of ideal polyhedra in this space HP3. Okay, now one thing I'd like to mention also is that, you know, I mentioned this result on polyhedra inscribed in this two-shaded hyperboloid, and there the result is the proof is similar, but it's a bit more exotic in the sense that you have to work with polyhedra in this extension of hyperbolic space by the de Sitter space. Of hyperbolic space by the de Sitter space. No, you really play with this geometric space, which is basically has one copy of hyperbolic space here, one copy of hyperbolic space here, and it has a copy of the de Sitter space here. And this is a space where, you know, you can do geometry. And you can consider the data on the boundary of an ideal polyhedron, and you can prove things there.
So this is a space that only has piecewise.
Yeah, exactly. When you go to the ideal boundary, you know, you have something quite funny happening. So suppose you take 2 points here and here, and you take the segment joining them. Then, of course, there is no way to define the length of this segment in the usual space, in the usual way, because if you try to integrate the distance element, I mean, this goes to infinity when you arrive here. But there's still a well-defined notion of distance between the 2 points that you can define by some algebraic formula, what is called the Hilbert distance, basically. So you can still define this distance, but not by integrating the infinitesimal distance. In other terms, you have compensation between what happens on the two sides of infinity. Yeah. Go ahead.
I don't understand what the picture is.
Oh, I'm just saying that we work with this geometric space.
Maybe I should ask you later what the space is.
Okay. Yeah. I'm going to tell you after the talk, maybe. Okay. So basically, so now if you look, we can look at polyhedra in this space. So we have polyhedra, we have edges, which are either hyperbolic geodesics connecting 2 points of the ideal boundary of one side, or they could be time-like geodesics in the de Sitter space. And the faces are also different types. They can be modeled on the, sorry, they will be modeled on the similar space but in dimension 2. So the extension of H2 by ds2. And then the combinatorial description of those polyhedra follows exactly basically the same idea. You can characterize the possible dihedral angles on those spaces. Right. And then the point that we still have to understand is, this last question that was what are the combinatorial types of the polyhedra which are weakly described in a one-sheeted hyperboloid? And then the corresponding question is what are the possible combinatorial types of polyhedra? What are possible dihedral angles of ideal polyhedra in the extension of ADS by itself? Because this picture that I was trying to describe here, we also have it for the anti-de Sitter space, where this ADS space has, in the projective model outside of the quadric, there is another copy of ADS. So it's an extension of ADS by another copy of ADS. And there, we don't know what the possible dihedral angles are. And we didn't really work on this enough, I guess. I think I'll stop here. Thanks a lot for your attention.
Any question or comment?
Yeah.
Well, I think that most of the questions you were studying, whether something is inscribed, can be treated as a one-dimensional higher analog of the Ptolemy. So we have the Ptolemy relation, and the Ptolemy relation is in the center of everything. I mean, it's related to, and I think that all those equations, whatever way they are written in length or dihedral angles or whatever, should lead to generalizations of Ptolemy and other things. This is the first question, or maybe comment.
Yeah, that's a very good remark. Yes, you're right.
Yes, and the second remark is, or maybe question is, that you mentioned the sixth circle theorem, which seems to be the theorem is that if 5 cross ratios are real, then the sixth cross, then their product is real. And there are lots of theorems like that, and they are all partial cases of one major theorem. There is a beautiful paper on that.
Yeah.
And my question is, so that happens for the complex plane, and I wonder whether all such things can be generalized for de Sitter or other planes. So when we deal with, not with complex numbers, but with maybe something, not numbers, but something similar, so that inscribedness or other conditions.
So I think the answer here, I can tell you one thing that is positive. So you're right. If we look at things inscribed in a sphere, we have things on circles in the sphere because the faces of a polyhedron inscribed in a sphere are circles that intersect at the vertices. And their intersections, or the fact that two circles intersect, can be written in terms of cross ratio, of complex cross ratio in CP1. And the point is, if you're also in this one-sheeted hyperboloid, you can actually use the same arguments, but instead of having complex numbers, you have what are called Lorentz numbers. So Lorentz numbers are basically numbers of the form x plus tau y. So you work in this space of x plus tau y, where x, y are real, and tau squared is equal to 1.
Okay.
Yeah, and you can do all this. And in fact, in the half-pipe case, the cylinder case, the same, but now you have tau squared equal to 0.
Great.
Yeah, so everything can be, this whole thing can be done in this setting. Anyway.
Thank you very much.
Yes.
Hi, so I found it very interesting. I had a question. So, from what I understood, you can actually deduce from this that if you consider the 3 connected planar graphs, almost all of them actually cannot be inscribed in any quadrics.
So in what sense you mean almost all?
So you consider how many of them there are on n vertices.
Yeah.
You consider the proportion of them which can,
Okay.
and that number should go to 0.
When the number of vertices goes to infinity.
So I think that follows from your statements about one of them is you require a Hamiltonian cycle.
Yeah.
And the other one is you require 2 cycles to partition the two in the 2 sheet.
Yeah. That's except maybe in the sphere case, where you just have this condition on. But in the other 2 cases, yes, that's absolutely.
Okay. Yeah. So I think that.
Yeah. Yeah. That's right. That's a good point. That's a good point.
And then just one other remark. It's true if you add the condition that the graph is 4 connected.
Yeah.
Then you get this theorem of Tutt that allows you to find a Hamiltonian cycle in polynomial time.
Okay, I didn't know that.
So that could be, if it's 4 connected, that's true.
Okay, I didn't know that. That's okay. That's nice. Thanks.
Just maybe as a low-level question, but what happens to the polytopes under Minkowski with respect to under duality with respect to the Minkowski metric? So I replace a point or a vector with a dual space, which is.
Yeah. So that's exactly the duality. Basically the duality works exactly in this way. So if you have let's say an ideal polyhedron, I should maybe erase. Yeah, thank you. So I think what you're describing is actually the duality that we use. Basically, if we, I'm going to draw it in a slightly different way, but it's exactly the same duality. So whenever you take a point in hyperbolic space, there is this dual plane. I'm going to draw this in 2D, right? So there's a dual line, and if you have a point in the zeta space, there is a dual hyperbolic line. So it can be defined exactly in the way you describe it in terms of orthogonal to lines or to hyperplanes. Now, if you have an ideal, maybe I should erase this. Have an ideal polyhedron. Well, I should just say first that the limit case of what I'm saying is that the dual of a point at infinity is a line tangent to the sphere or plane tangent to the sphere at that point. And therefore, if you have an ideal polyhedron, I'm sorry for the simplicity of my drawing, the dual will be some polyhedron which is outside of the sphere. So basically, again, you see this duality between objects in H3 and object in the zeta space. So this duality has beautiful properties, but one key property is that for every edge there is a dual edge, and the edge length of this primary edge is equal to the length of the dual edge, and that's what makes everything work in a way.
And also, have you tried to see how to work things like spin structure into like tackling the problem with the weakly inscribed polytopes? Because you have these true sheets, and I guess if you look at the monodromy group, you can resolve some of the projectivity.
So okay, I think there are some things, but I think they're going out of the topic of the talk. We can maybe talk about them later, because I think there are lots of interesting things.
I just mean like build this spin structure in by like maybe instead of, I think sometimes when you do the calculations, take absolute values, and maybe if you keep track of the signs using the Minkowski norm,
okay,
you might be able to see something. I'm not entirely sure, but yeah.
Okay, I think that's, I don't know. That's interesting. Yeah. Thanks a lot.
We didn't consider the case that the Polyhedra is described in a paraboloid.
Yeah, paraboloid. So no, the paraboloid is also projectively equivalent to a sphere. So basically, if you take a sphere, you send one point at infinity, but the plane at infinity is tangent, then you find a paraboloid. So it's the same situation. Yes.
Okay, time is over. So let's thank the speaker again.
Thank you.